Hi guys, and welcome back to the sixth video tutorial. First we just need to use the push instruction. As you can see in this picture, there is push RM16, RM32 and RM64. They take as an operand or parameter a register or a memory location. That is what RM means. The 16, 32 and 64 means whether the register or memory location is 16, 32 or 64 bits. So these three instructions list all the same opcode if you see FF/6. So the difference between push RM16 and push R16 is that the first form of the instruction also supports memory locations, not just registers. However, the first form has a disadvantage that the instruction also takes one more byte of machine code because it requires an additional mod RM byte. And the remaining 6 forms from the table of the push instruction are not so relevant now as they only apply to segment registers, which are not used by normal Windows applications. Also, please note that in Intel format, the least significant byte is stored first and the most significant byte is stored last. Therefore, the number 1020E000 becomes 00E02010. So Intel uses the so-called little endian format. And also note that there is no push RM8 because the stack is always aligned to at least 16 bits. Therefore, you cannot put 8-bit values onto it. And also note we can do this inside a remote target process from our local process because the stack of all threads of a process is stored in the same virtual address space as where the PE file itself is loaded. So every process has exactly one virtual address space. For example, in 32-bit mode, the virtual address space is from 0x00000000 to 0xFFFFFFFF. That is about, I think, 4 GB of memory. So if a process only has one thread, there is only one stack. So with FF/6, the 8 bits of the first byte are not enough to store the actual opcode. So it takes 3 bits from the following mod RM byte to store additional information. Since you can store a number between 0 and 7 with 3 bits of information, the number after the slash is always a number between 0 and 7. And the remaining 5 bits of the mod RM byte are used to specify information on where the value is stored, whether it is a register or a memory location. So when you see a slash in an opcode, that means that it uses a mod RM byte. And note that the contents of the DLL main get loaded only its 32-bit address, so the EX register can store the whole code of the function of the DLL main because it is larger than 32 bits. However, it can store its 32-bit address. That's why we're gonna use machine code. And we also gonna use the EMM32 where it says 68 ID. ID comes from immediate D word, which is a 32-bit value. IV is immediate word, which is 16-bit value, and IB is immediate byte, which is 8-bit value. We're just gonna write here 0x68, then 0xDB, and we're just gonna copy paste this 3 times more. So this is actually equivalent to push like this. Here is 0x. So here is 8. Okay, then we need to do this again and again and again. So 4 times. So we're gonna push onto the stack these values. These values are just placeholders for now. Then we're just gonna move everything inside the EAX using 0xB8. Check the table. So we don't need this. Okay, so it's just gonna, this is not push, this will be move inside the EAX, and then we're just gonna jump to the EAX because we need to return our DLL main function. Check the table, it's gonna be 0xFF and 0xe0. Okay, this is just move not move, this is jump to ex. Okay, note we still didn't do anything, we just created a byte array with machine code. These are just placeholders, yeah, and then we're gonna move everything inside the eax, and then we're gonna jump to eax. Okay, now it's time to actually populate these placeholders. So remember what we need to add via machine code onto the stack. We need to do it in reverse. Code plus 1 will be equal to 0. But we cannot just do it like that. We need to actually typecast everything as a PD word. Here another parenthesis. And as a pointer. Like that. So code plus 1 means this one. This one will be equal as a D word, which is 4 bytes with 0. We're just gonna copy paste this. It's gonna be code 6. Code 6 is here. This will be equal to 1. So this is third parameter from DLL main. This is the second parameter from DLL main. I think if I write it like that, you might understand it better. Okay, this will be 11. So 11 is actually here. So this one will be equal to the first DLL main parameter, which will be the image base itself. So in order to do that, we're just gonna write it equal to destination image base, but we need to typecast it as a D word. So this is the first parameter from DLL main. Actually, it's not from, this is for. Once we did that, we need to move to the code plus 16. Note code plus 11, which is this one, is equal to destination image base as a D word. So as I told you, D word will occupy all 4 bytes. So this one will be equal to our external function, this fun entry that we are calling it with run DLL32. So how on earth can we do that? Because I was thinking and I thought it might be hard doing it, but I figured it out. Once our DLL is injected inside notepad.exe and we relocated all the sections and everything, now the address in the virtual space of the notepad.exe from our DLL main of this exported function, it has changed, of course, and we need to get that address. In order to get that address, we just gonna go after we copied the sections here. Oops, I forgot here to put plus plus. In order to get our exported function, we need to go inside the image directory entry export. Create here a variable type image pimage export directory. Let's just call it pimage image export directory, which will be equal to something that might be very long. Let's see. So I'm just gonna typecast it as a pimage export directory. Here will be the DLL buffer. If you remember, we need to typecast this as a D word. So DLL buffer plus. Here we need the virtual address of the image directory entry export, but we actually need the raw address, not the virtual address. So for that we're gonna create a function. Just gonna write a function of type D word. So we're just gonna use convert virtual address to raw address, and here we get as a D word the virtual address, and as an LP void, I don't know, the file, let's say. So we need to get the pointer to first source image section. So p-image section header DOS header, which we need to typecast p-image section header this file. Then we need another p-image section header variable type. Just call it section. Again, we're gonna typecast it to p-image section. And this is similar to what we have written before, so will be file plus from DOS header this ELFA new. Okay, here is plus ELFA new plus the size of image anti headers 32. Okay, something like that. Here we need to typecast it as a dword, the file. This is image DOS header, not section header. Sorry. Okay, so the code should look like this. Okay, and after that we just need to go through all the sections until the appropriate section is found. So we do that in a while loop. So while the virtual address is greater than section virtual address plus section misc and virtual size, just gonna do the section plus plus. Okay, after we have found the appropriate section, we store it in a dword, the offset, which will be virtual address minus the virtual address of the section, and then the raw address which we want. This is why we created a function. So raw address will be this offset plus the pointer to raw data from the section. So section pointer to raw data. Okay, and we're just gonna return this raw address. So our function to convert the virtual address to a raw address it will look like this. Okay, once we have done that, we can successfully get our exported function address from within inside notepad.exe after we have injected it. So here we're just gonna call convert, and the parameters will be as follows. We need to get the virtual address of this image directory entry export. We can find it in optional header data directory. I believe that's the index 0, the first directory. So DLL image anti headers, optional headers data directory, then it's gonna be image directory entry export virtual address. Okay, and the second parameter will be just the DLL buffer. I believe we called it DLL buffer. Yeah. So this is how we get the actual image export directory. We need to create a pointer to this image export address table. So pdword, let's say PEAT, which is going to be equal, I'm just going to typecast it as a dword pointer. It will be equal to this DLL buffer plus, we're going to use again our function convert virtual to raw address. We require again two parameters here. The first parameter will be out from this image export directory the address of functions, and the second parameter remain the same, the DLL buffer. Okay, Don't forget here to typecast the DLL buffer as a D word. Now we have a PD word, so PEAT 0 will be the first exported function. Okay, and then PEAT1 is gonna be the second exported function, and so on. We can check our DLL which index has this fun entry exported function. So export directory, and we see that our fun entry, it's located at first index and the second is the main entry. So we're just gonna use the PET0. So now we have the exported function. We go back to our machine code, and code plus 16 is this one. It will be equal to that exported function, but we need to do it like this, plus that PET 0, code plus 21. So 21 will be this. So we still have this placeholder to change. This is the exported function. Here will be the exact address point. So this plus DLL image NT headers. From the optional header we get the address of entry point. We are not finished yet because we just declared the template. We populated the placeholders with the right values, and now we just need to write all this code inside our target process. So to do that, first we need to allocate this much size inside the target process using virtual alloc ex. I'm just gonna store that as an lp void. So lp void address buffer gonna be equal to virtual alloc ex target process null size of the code, and then here the allocation type is just mem commit, mem reserve, and page execute read write. We're gonna write this whole machine code to notepad.exe in our case. We're gonna use write process memory, but we're gonna store it in a bool value. So bool success write process memory. So inside the target process we're gonna write this address buffer. The code is the actual buffer, size of this code, and here again just null, and that's it. If success equals to true, we just set the EX register to this new address buffer. So context EX register out equals to this address buffer, but as a D word. I'm still thinking on something while I'm writing this code. I believe here the exported function is the at index 1, not 0. Once that's finished, we just gonna set the thread context and resume the thread. I'm just gonna go back to our DLL inside the fun CPP, and here we just wrote inject DLL inside remote process. Here we actually gonna write that function. I'm just gonna call here include tools. I believe there is inside also the Windows H, and here I'm just gonna write tools auto inject. Here we need the process and our DLL. path. So the process, I'm just gonna define it here, lpstr target path gonna be equal to something. So this is how we call our function. I'm just gonna write here C Windows System32 Notepad.exe. Okay, note I am using the 64-bit version of Notepad, but my DLL is a 32-bit. I'm just gonna leave it like this, and I'm gonna show you what will happen. So I'm just gonna go here on the solution, and I'm just gonna rebuild the solution. Okay, we have here an error because we just need to define it as in tools.h, this function. So inside tools.cpp, I'm just gonna write here tools, like that. Don't forget this return 0. Don't put it here. We're gonna put it after we get out from this if statement. Also, we have forgot something to actually read the DLL inside buffer. So where we get the DLL image DOS header, we just gonna use read file. So DLL file, DLL buffer. Inside here we're gonna store all this. The size, I'm just gonna declare here a SS difference, and here is null. So dword SS equal to 0. Bool DLL red, and here if DLL read equals true, you can just do all this code. I'm just gonna remove this, and I'm gonna put it here like that. Make sure it's equal to 0. Also, please don't forget when we get the fun entry exported function address here, make sure where is the first parameter from the convert virtual address, just typecast it to dword. And here also, when we do the base relocations, make sure you do until a is less than the relocation counts. Also here, when we declare the patched buffer, this will be the one that's gonna be incremented with the delta image base and not the patched address. Also here, when we were writing the machine code, after mem commit flag, we need mem reserve, not mem release. So I'm just gonna use ethical injector to inject the DLL inside the loader, exactly what we did in the beginning. Okay, right now I'm gonna copy this, or I'm just gonna move it, create here a new folder on the desktop, and watch this. This is very scary and crazy in the same time. Please use this only for educational interest, only for educational purpose. No black hat activity is allowed. So with that being said, watch this. Now if we inspect the loader, inside the last section there is our DLL. Remember, our DLL has inside the function that inject itself further. So when I double click on this loader, it's deleted itself. Before it deleted itself, it called rundll32.exe to execute the DLL that the loader has been exported to appdata. And now the DLL is running inside rundll32.exe, and from there it will inject by itself inside notepad.exe. When I click OK, you can see here down it's a notepad icon appeared. When I click it, it says from FunDLL I am inside C Windows WoW 64 notepad.exe. So if I cannot close it because there is a while true loop, as I told you, but right now our DLL is inside notepad.exe. We can use it, we can verify that with process hacker or process explorer. I'm just gonna put this away. So we go here, we can see there is a notepad process. We can even right click on it and open file location, and we can see that this is a valid notepad process being ran from the 32-bit version of the pad, and it is actually our code, so it's our DLL. If you want to find our DLL inside the notepad, you just right click on the notepad process, we go to properties, and on the memory tab we just search the RVX protection. This is read write execute. You remember we use that a lot. So I don't think it's this one, this is just 4 kilobytes in size. So there is another RVX with 304 kilobytes. So we go on this little arrow, we double click here, and as you can see, this is our DLL. It starts with MZ. So this is our legitimate DLL. Our DLL now hides inside Notepad at this base address. You can try and verify if this is the legitimate DLL that we were coding by just saving this part of the memory on a desktop as an .dll file. Okay, and then you can just right click and view it with CFF Explorer. That indeed is the right. If I right click on the notepad and terminate, it will close our program. So we didn't just created a process and renamed it to notepad and we run our code. This is actually the exact legitimate process of notepad, and our DLL executes inside like an executable using machine code. Notice how we declared here C Windows System 32 Notepad, but it actually executed the Notepad from SysWow 64, which is the 32-bit version of Notepad, because this is how Windows Image Loader behaves. In the next tutorial, instead of doing this while through loop of showing a message box, we actually gonna open a socket communication using TCP protocol from within inside this notepad, which is interesting. So if you like this tutorial, please stay tuned for the next video, and also please like and subscribe. Bye.